For this exercise, we're going to continue integrating these three. However, for this first integral, we will have to use a trigonometric identity, that is the power reduction formula for sine squared, that is 1/2, or rather sine squared, 1/2 1 minus cosine 2 theta. That is, we reduce the power at the cost of multiplying the angle, but that should be no big deal because that problem is easy to solve because that will require a baby u substitution that we don't even need to show, all right? So let me do that replacing here. So let me continue. That's equal to 8 times the integral from pi over 6 to pi over 2 of 1/2. Let me use it. Same color. 1/2 1 minus cosine 2 theta d theta minus 2 times the integral of pi over 6 to pi over 2 of sine theta d theta, and minus the integral from pi over 6 to pi over 2 of d theta. Well, before we can integrate these guys, we will have to split this into two integrals. Number one, I'm going to divide out the 8 with the 2. That's going to be the integral from pi over 6, or 4 times, to pi over 2 of 1 minus cosine 2 theta d theta minus 2 times the integral of pi over 6 from pi over 6 to pi over 2 of sine theta d theta minus the integral of from pi over 6 to pi over 2 of d theta. Well, in this case, this is what we're going to do. So we are going to combine, or to distribute this into two integrals. That is 4 times the integral from pi over 6 to pi over 2 of d theta minus 4 times the integral from pi over 6 to pi over 2 of sine theta d theta, and oh no, that's actually cosine 2 theta first. And let me make some room over here. Need some. And the remaining two integrals, minus 2 the integral of sine theta d theta minus the integral of d theta, both from pi over 6 to pi over 2, pi over 6 to pi over 2. All right, so before integrating this, actually we can combine like terms, because these two integrals, notice they are the same integral. This integral right here and that integral there. 4 integrals of dt minus 1 integral of dt, that's going to leave us with 3 integrals of dt. And d theta rather, not dt. So that's going to be number 1. That's going to leave us with 3 times the integral of d theta minus 4 integral of cosine 2 theta d theta, and minus 2 times the integral of sine theta d theta. And well, so that's okay, again the limits, pi over 6 to pi over 2, pi over 6 to pi over 2, and pi over 6 to pi over 2. And we may go about the integration here. So integrate d theta, well, that's just theta, and that's going to leave us with the quantity 3 theta minus 4 times 1/2 sine 2 theta. And the integral, careful, because the integral of sine, which is negative cosine, times the negative outside becomes a positive 2 cosine. And that gets evaluated between pi over 6 and pi over 2. And well, the rest of the story from here, fundamental theorem, upper limit minus lower limit. That is 3 times pi over 2 minus 4 over 2, which is 2 sine of pi over 2, and plus 2 cosine pi over 2. That's the evaluation of the upper limit. Now we need to do the evaluation at the lower limit. That is 3 times pi over 6 minus 2 sine pi over 6 and plus 2 cosine. Oh, actually, I think I'm missing a coefficient here. I'm missing the 2 here, the coefficient 2 for the integral of cosine 2 theta, which is sine. And so that's, give me 1 second here, 2 pi over 6, actually. And that's 2 cosine of pi over 6 also. Okay, so let's evaluate this. So number 1. This is essentially sine of 2 pi over 2, which is sine of pi. That's going to be big 0 here. That's a 0. That's cosine of pi over 2. That's also 0. And, well, in this case, 3 pi over 6, well, 3 times pi over 6, well, that's pi over 2. Well, that reduces to, this reduces to pi over 3. And sine of pi over 3, that's actually going to be root of 3 over 2, and cosine pi over 6, that's root of 3 over 2. All right? So in this case, let's combine this and actually see how these terms are going to get zeroed out, because this root of 3 over 2 times negative 2, and then this root of 3 over 2 times positive 2, these two quantities are going to get canceled. Well, let me write the whole thing so you can see what I'm talking about. Well, so this is 3 pi over 2 minus 0 plus 0, and then minus pi over 2. And that's going to be negative 2 root of 3 over 2 plus 2 times root of 3 over 2. You know, this number gets multiplied by the coefficient, and actually, since these are opposite signs, they have opposite signs, they just cancel. And 3 pi over 2 minus 1 pi over 2, that's actually 2 pi over 2, which reduces to pi. All right? And that's final answer for this area between curves problem. And we will go about the last topic for the section, which is also the last topic for the semester, which is arc length in polar. So let's look at one example. Let's look at the formula. Well, it looks a little similar to that in parametric form, except that instead of having the derivatives of x over with respect to t and the derivative of y with respect to, well, it looks a little different. We're not going to do the derivation. It's going to take too long. We're just going to use this formula, right? Ultimately, you won't be asked to derive anything or to prove anything for this course. So just to briefly describe the formula, well, this r is the actual function of the actual r, which is the function of theta, and this dr d theta, it's the derivative, the first derivative of that given function of function r of theta. All right, that's all it is. And well, you will be given an interval to integrate over. And well, these ones may be a little tricky, and well, you'll see what I'm talking about when we get to finish this integral. And yes, I mean, the most natural thing to do when it comes to a problem like this is to set up an integral using these limits, which is fine. That's fine. However, you'll see what's going to happen later. So let's find the derivative dr d theta, the derivative of 1 plus sine, that's a cosine theta, and well, also between 0 and 2 pi. And let's set up the integral. So that is L, that's going to give us the integral from a to b, or alpha to beta, either way. That's the square root of r squared plus the derivative squared. Well, in this case, d theta, right? So this is what we do. Substitute the original function over r and substitute the derivative where it corresponds. It's very formulaic. The rest, of course, will be integration. You'll see. So number one, that's going to be the integral from 0 to 2 pi for now of the square root of the original function, that is 1 plus sine theta quantity squared plus the derivative squared, that's cosine theta quantity squared d theta. And then from here, well, let's expand the binomial. The integral from 0 to 2 pi square root of 1 plus 2 sine theta plus sine squared theta. This is one way to expand the binomial by using the formula, or do the product of this quantity in parentheses by itself and FOIL it. Either way, it should give you the same answer. Either way is acceptable to do, all right? I do it this way because I think it's quicker. And then that plus cosine squared theta. And no, do not attempt to integrate this madness right now, because set you that whole madness inside of the radical, well, just think of the derivative of that. We don't have anything outside multiplying with it so we can actually work a UDU. So no, it's not going to work. Reduce. Well, from here you can see that sine squared plus cosine squared equals to 1. And you can also see that 1 plus 1 equals to 2. All right, that's the integral from 0 to 2 pi of the square root of 2 plus 2 sine theta d theta. All right, so this is the simplest we can get about this integral. However, there's not much we can do about it in this form because, well, again, try to use your favorite technique of integration. Well, I guess use substitution. Well, if we said u equals to 2 plus 2 sine, the derivative would be 2 cosine. But unfortunately, again, we don't have a factor of cosine multiplying with the d theta, which stands the du part of the problem. So no, we won't be able to use u substitution yet. We will, but not right now. How do we go about it then? Well, what's the real trick here? Well, I mean, in other kinds of problems, typically a good way around this is to find an algebraic technique. You know, in a similar way that when you learn to calculate or to evaluate limits, you use a bunch of algebraic techniques, such as factoring a polynomial. But well, that's not a polynomial. Maybe rationalizing a denominator or a numerator. Well, that could be the case, which involves some conjugate, and in this case, that's what we're going to use. Multiply numerator and denominator, but which denominator anyway? There's a denominator, of course. When you don't see anything, the denominator is always 1. All right? And, well, so in this case, we're going to multiply by the conjugate, by the trigonometric conjugate, which is essentially at the same time rationalizing the numerator. So let me write the whole thing again. That's the integral from 0 to 2 pi. And, well, the same, square root of 2 plus 2 sine. Over 1. And, well, I'm going to multiply by the same quantity. 2 sine. 2 sine. But in this case, the conjugate would be having the opposite sign in the middle, right? That's what the conjugate is. And times d theta. And of course, okay, let's multiply things together. Number one, well, for the denominator, I'm just going to do the multiplication across. 1 times the radical, this is simply the radical, 2 minus 2 sine theta. And in the numerator, well, what do we have? We have the product of the radicals. The product of the radicals is the same as saying the radical of a product. Now, well, it looks like we're making this a lot more complicated than it initially was, but trust me, this one is going to reduce a lot nicer. You'll see. Well, one thing to identify here is the form that we have inside of the parentheses, and ultimately that's the purpose of rationalizing a denominator or a numerator which involves a multiplication by a conjugate, because the product of two conjugate binomials is the factor form of a difference of squares. So what do I mean by that? Well, let me make some space over here first, and you'll see. So essentially, we have the form a minus b, a plus b times a minus b, which is the result of factoring an a squared minus b squared. Typically, we go from right to left. We are given a difference of squares, and we factor it the product of conjugate binomials way, right? Not the other way around, but this time we're going to do it the other way around, especially because, well, you'll see why. So that's going to be 2 squared minus 2 sine squared. The denominator remains the same. All right, so let me simplify this. 0 to 2 pi, 0 to 2 pi. And so that's going to be the integral of 4 minus 4 sine squared theta. Is this really simplifying? Yes. 2 minus 2 sine. And d theta. Okay, so number one, I would like to factor the common factor in the inside of the radical in the numerator. That's going to be 0 to 2 pi square root of 4 times 1 minus sine squared theta. And there's a couple of things that we're going to do here in the numerator. So that's 2 minus 2 sine. Number one, this is a product of the radical of a product. That means we can take the square root of the two products. Well, I'm not going to take the square root yet. However, I think you can see something pretty interesting here. What is this 1 minus sine squared? Cosine squared, all right? Okay, so that's cosine squared. So that's the integral from 0 to 2 pi of the square root of 4 cosine squared theta 2 minus 2 sine theta d theta. And notice how the quantity in the inside of the radical in the numerator, it's a perfect square, which reduces to 2 cosine theta 2 minus 2 cosine theta. And now, oh wait a minute, that's sine. And now, what did we do? All this trick that we did is to finally get this cosine multiplying with the d theta, so we can use a u substitution, which is something that we initially didn't get the chance to do because we didn't have that cosine. So now, after all this magic here, it's there, all right? And we may go about the integration here. We may go about the u substitution. Okay, let me continue on the next page. I'm afraid I'm not going to have enough space for this. Hold on. Okay, yes, that's fine. Yeah, let me go to the next page. Let me actually move this to the next page. So let's do the usual. I mean, what could go wrong about it? I mean, so from here it should be, it should be just straight to the final answer. U equals to 2 minus 2 sine theta, and du equals negative 2 cosine theta d theta. All right? And well, we have the, let me solve for 2 cosine theta d theta. This will be negative du. All right? This whole thing will be negative du. And we'll recall that whenever we are evaluating a definite integral using u substitution, we do a u substitution not only for the variable part, but also for the limits of integration. Well, so number one, let's see what we got for now. Number one, we have the integral. I'll figure out the limits of negative du over the square root of u. Okay? But now we need to figure out the limits in the world of u. So those limits are going to be, well, number one, u of 0, which is 2 minus 2 sine of 0, which in this case is 2. Because sine of 0 is 0 rather, times 2, that's still 0. 2 minus 0 is 2. The upper limit in the world of u, that is u of 2 pi. That's 2 minus 2 sine 2 pi. And well, sine of 2 pi again happens to be a 0. Times 2, that's still 0. 2 minus 0 equals to 2. Okay, let's go back to the integral. What's the integral of negative du over the square root of u when we go from 2 to 2? Huh? 0, right? This is not generating any area, right? But hold on. In accordance with the picture from the problem, we're seeing an area, right? So how come this area is 0? Well, so we need to redefine the limits of integration. We need to rework the limits. We need to have a second look at a region over which we are integrating. So this is not the way for now. What are we going to do then? Okay. Like I mentioned, it's very natural to just use the limits of integration as being those from the region in this case. All right. I mean, this region traverse once. I mean, makes sense to go from 0 to 2 pi. However, the way we're going to redefine this is by instead. Check this out. So we're going to go from this ray, which is negative pi halves, all right, and we're going to go all the way to pi halves, and that number we're going to multiply by 2, because again, if you go from negative pi over 2 to 3 pi over 2, I'm pretty sure you're going to get a 0 as well. So instead, we're just going to take half of the arc length, and whatever result we get, multiplied by 2. Again, I think this is something I mentioned last class. When we're working in the world of polar system, there's weirdness. We usually run into this kind of weirdness as opposed to working in rectangular, which in many cases we don't get these weird things. All right. So let's see. So let's redefine the integral, and again, so I'm going to rewrite the integral. So that's the integral from 0 to 2 pi of 2 cosine theta d theta. The d theta goes up, and root of 2 minus 2 sine theta. And that equals to 2 times the integral from negative pi over 2 to pi over 2 of 2 cosine theta over the square root of 2 minus 2 sine theta. Now let's use the same u substitution. I'm going to do the whole thing again because I already crossed everything out from the previous part. And That's u equals 2 minus 2 sine theta. Du equals negative 2 cosine theta d theta. That means 2 cosine, the same thing, theta d theta equals negative du. So the first three lines from the previous substitution remain the same. That's fine. However, now that we have different limits of integration, you'll see what's going to happen. So that's a u of negative pi over 2. That's going to be 2 minus 2 sine of negative pi over 2. Well, number one, what's sine of negative pi over 2? Sine of negative pi over 2, which is the same as saying sine of, what's this? 3 pi over 2, isn't that a negative 1? So negative 1 times negative 2, careful, that becomes a positive 2, which is 2 plus 2, which equals to 4. The upper limit, u at pi over 2, positive pi over 2, that's 2 minus 2 sine of pi over 2. And well, what's sine of pi over 2? That's positive 1. So that's going to give us, well, 1 times negative 2, that's negative 2. 2 minus 2 equals to 0. And those are the new limits of integration. So number one, that's 2 times the integral from 4 to 0. I know this is weird because we're getting a smaller, a larger lower limit than an upper limit. That's fine. You'll see how everything is going to work in the end. So that's a negative du. In fact, that negative sign that you see there, you can use it to reverse the order of the limits. That's totally fine. That's one of the properties of integral you learned back in Calculus 1. And well, from here, let's just integrate this baby here. So that's a negative 2 integral from 4 to 0 of u to the negative 1/2 du. And if you're still a little uncomfortable with the limits of integration, well, change them from 0 to 4 and use that negative sign. Don't write that negative sign anymore. That's u to the negative 1/2 du, and simply add 1. So negative 1/2 plus 1, that's 1/2 over 1/2, and evaluate this from 0 to 4. And well, dividing by 1/2 is the same as multiplying by its reciprocal, which is 2, and 2 times 2 equals to 4. And I'm going to write this u to the 1/2 in radical form, that is the square root of u. And again, the advantage of changing the limits of integration to the world of u is that we don't have to do the back substitution and use the fundamental theorem on a larger expression. In this case, all we do is use these limits on the function of u. So that's the square root of 4 minus the square root of 0. And the square root of 4, which is 2, minus 0, that's 4 times 2, which is 8. And that's final answer. So again, I think this last problem was really good because it gives you an idea of the weirdness that we usually run into when we work in the world of polar coordinates. In some cases, like in this situation, we have to essentially redefine the limits of integration. Yes, still based on the same region, just do a little trick to make this work, because otherwise, I mean, this integral from 2 to 2, which gives us a 0, well, no, that's not the solution. Clearly, there's some, well, I think I mentioned area before, but we're not looking for area. We're looking for arc length, not area, right? I'd rather take that back. So, and in this case, well, this is not the actual answer, so there has to be a way to rework this problem, all right?